when you are at a state that has nitrate problems, right? You think about, okay, what can I do? What can I do? And then so you go back to some of the old data that you gathered during your grad school, right? You never had the opportunity to actually like analyze that data, so that's what I'm presenting today. Characterizing of field denitrifying bioreactors that I had been working on like for at least 6 years in grad school. So here is an example of like what Jill kind of like also presented. We have an increasing nitrate concentrations in the state. So that can be a challenge, and also there is an exchange between groundwater and surface water, so I would anticipate a similar kind of trend for nitrate concentrations. So I don't go over like what nitrate can cause, what problems, environmental problems, or human health problems, because Jill kind of covered, Dr. Coleman-Bassett covered everything. So Wisconsin has quite a number of, quite like a good portion of tile drainage systems. These drainage systems, you know, in the old days when in the spring the soil was really wet, so you had to find like a way to remove that water from the soil, and then tile drainage systems are applied to get rid of that water. So the thing about them is that then you have an outlet for water. So that's a very nice place if that water is contaminated to put a remediation system on, right? So about in some eastern Wisconsin areas, 5 to 60% tile drainage agricultural system exists. So then that's what we did. So we put these denitrifying bioreactors on this edge of the field tile drains where like the good thing about nitrate is that it can be remediated. So it has a gaseous state, right? So from nitrate to nitrogen gas, that's the process of denitrification. So if you provide that environment where that denitrification can happen, that's great, right? So we practically put these boxes on the ground and we divert the water from the tile flow into these boxes. We provide the food for microorganisms like anaerobic conditions and food, the wood chips or like something similar that would provide the organic matter, and we'll wait, right? We'll wait to see and monitor the system to see if it actually is working. And a lot of the performance that we could impact on is that how big we build that box, right? If there is enough time for denitrification to happen. So that's the question that we should be able to answer based on the observations that we make, hopefully, right? So then here is the formula for hydraulic retention time, which is the porosity of the system multiplied by the volume of the reactor divided by the Q or discharge that's coming from the tile. So then we built these reactors, right? Practically a big pit, and then kind of like diverted that flow into that pit, covered, like put like the wood chips or the substrate in, and then covered it with soil. And then so here you can see the two outlets, here and here, like this is the outlet from the field, right? The input of the tile drain into the reactor there, and then here is the outlet from the reactor where we got the samples from. So like we had quite a number of those, 9 reactors at 6 field sites. And we monitored them for about 1 to 6 years, depending on the location. And we had them at New York State. And then, so we got about like more than 1,000 samples, but 561 sampling events. So when we go to the field site, take the water sample or samples and then analyze them for nitrate, sulfate, dissolved organic carbon in some cases. And then we also measure the flow rates, temperature, the things that you should measure to be able to do that characterization. So here is a typical kind of like type of data that we got. This is for like one of the sites that we had. The top graph shows the temperature. Water temperature in the tile lines, you can see during the summer, of course, we had the increase in water temperature. and then decrease during the winters. And so, like you can see that we had some gaps in the data when we didn't have funding. So as soon as we acquired new funding, we would go back to the field and do the rest of the analysis. The second graph, the y-axis shows the discharge, the x-axis also is showing the time. So the discharge, I put it in the log scale because, like you can see, it's very variable. Of course, during the summer when it's hot and we don't get enough rain, but during the winter, we also don't get a lot of like flow, but somewhere in between, like in the spring and fall, of course, we have more rainfall events and therefore more discharge. The third graph would be the nitrate concentration. The black dots are the inlet concentrations, and the blue dots are the outlet concentrations. And it's a good thing that the outflow concentration is less than the inflow concentration, as you can see here. Here are the, like for the most part during the summer, we have 0 concentration of nitrate at the effluent of these reactors versus it could be very variable, but like sometimes you have high flow events during the fall and the spring, or during the winters when there's not a lot of activity going on. And the last graph shows C2CO concentration, which means like the concentration at the effluent of the reactor is divided that by the influent. If it's 0, it's really good. It means that 100% of nitrate is removed. If it's 1, none is removed. So you can see a lot of events we had like 0 concentration at the effluent of the reactors. So in fact, about like I believe about 50% of the data events or the sampling events we had 0 concentration or very low concentrations of nitrate at the effluent. Okay, here is a summary of that data from all the field sites that we had, right? So you can see somewhere between 57% removal of nitrate has occurred. So the blue lines are the inflow nitrate concentrations, and then the orange lines are the outflow nitrate concentrations, so in the different field sites. And then for some of the sites, we had only wood chips as a substrate. Sometimes like we kind of combine about 5 to 20% biochar to it. It's called the WB, so that's the biochar that we added. So you can see like the inflow nitrate concentration overall is about 10 milligrams per liter plus or minus 8 milligrams per liter of nitrate. At the effluent, however, it is about 5 plus or minus 8. So it's about 57% removal. And again, I want to mention that at this many events, like 260 sampling events, the outflow nitrate concentration was less than 1, which is a kind of like a limiting nitrate concentration. So we did some statistical analysis based on the kind of like observations that we had. So the outflow nitrate concentrations depended on the inflow, what was going in, nitrate concentrations. And then the temperature was important. HRT, the retention time, was important. Site was important. So it was important what kind of, where it was located. The bioreactor was located. That had an impact. Medium, like either we used wood chips or wood chips with biochar, was not as important or not significant, let's put it that way. Age of the reactor was not important. So these reactors that we had was about like from 1 to 6 years. There was no decline in the application or in the performance of the reactors up to 6 years. So I know these reactors can work up to 24 years with no problem. Maybe a little bit of decline, but up to 6 years, there's not a decline. And as anticipated, sulfate concentrations at the influent did not have an impact. And then you can do like, you get to do some sort of like statistical models, and then you can see like, I can come up with these equations, and you can like anticipate like what are you gonna get at the effluent of these reactors. The important part being like you can anticipate like with a very good R squared, like 84%, what is going to be coming out of these reactors. However, if you look at the formula, the site is important. And the site dependability kind of prevents us from actually like coming up with a criteria to be able to design these reactors for like different locations. So it would be really hard for us to kind of like say, you know, this is the formula you should use for this type of reactors, right? So here are some of the examples of if we put the C2CO on the y-axis and then put the HRT, the hydraulic retention time, on the x-axis, what can we come up with if you just use the first order reaction rate, right? Find the K potentially for these reactors. And you can see we can come up with various numbers of K. So they're varying from like 0.7 to or 0.51 to 5.73. So in some of the sites, we have like a very high reaction rates. In some others, we have a very slow reaction rate. So it would be really hard to come up with some of the criteria that we want to come up with. And the impact of temperature, that's also you can see, like, of course, we have an increasing trend during the summer months. The temperature increases, but also the flow rate decreases, right? So you both have a high hydraulic retention time, but also you have a high temperature that like potentially K or the reaction rate should increase. So in that case, it's like, again, the kind of like the impact of both retention time and K that you're kind of capturing. So we have a Q10 of 2, which means that like every 10 degrees increase in temperature, the reaction rate would increase about 2 times, which is within that biological like range that we would anticipate from 2 to 3 for Q10. The cost of these reactors is about like, I mean, when we were building it, or, you know, in 2023, if you can like, when you look at the resources, it's about 16K plus or minus 10K, which is quite a lot for farmers to be able to handle that. They last about 26 years, so about $53 per acre per year. And well, in the old days, 70% of the cost could be offset by federal government cost sharing. We should look to see like what's going to happen in the future, right, with the federal government cuts. And then other best management practices is kind of comparable to them as well. Like if we have constructed wetlands, it's about $65 per acre per year. Our saturated buffer also costs the same way. So if the land is a limiting factor, so the bioreactors could be an option to use. Okay, so kind of like a summary of what we discussed. Application is successful, right? We have 57% nitrate removal. However, it would be hard to come up with the design criteria because we don't know the exact relationship between HRT and the nitrate removal because it's so site dependent. And at the end, like when we are thinking about Wisconsin and how much nitrate can be an issue, could these reactors be a problem solver, at least in some parts of the state? So that's the kind of like the line of thinking I have right now. Thank you.